Okay, sorry for the delay. Okay, let's talk a little bit about more about the axiom of choice. Okay, let's prove. So a few more let me tell you another corollary. Okay, this is kind of like a corollary to one of the corollaries. So assume axiom of choice. And suppose A is an infinite set, then A has a countable subset. Okay. And the proof is well, there's like one way to prove it is, well, put A into like put a make A be well ordered. Okay. Find a well ordering on A. Well, if you do that, that means you have like the least element. You can write A as to be like the least element, the one after that, then A2, and so on. And then A might have more stuff, but in particular, you have a subset of A corresponding to the natural numbers. So the countable subset C is just A0, A1, A2, and so on. And A might have more stuff than that, but you certainly have a countable subset. Okay. And so it is weird. It's kind of weird. If you don't assume axiom of choice, you can't necessarily say that an infinite set has a countable subset. Another way to state this is that if A is infinite, then the cardinality of A is greater than or equal to the cardinality of the natural numbers. So the axiom of choice, you don't necessarily know that. Okay, what's another corollary? Choice. Then a countable union of countable sets is countable. A proof. We have a countable union of countable sets, so we have a set like S0, S1, S2, and so on. And each SI is countable. And our goal is to show that the union of all the SIs is also countable. Okay, so since SI is countable, we have little si from the natural numbers to SI, which is 1-to-1 and onto. In other words, this SI is a subset of n cross SI, or is an element of the power set of n cross SI. Okay. Okay. So this is, let me try to explain the problem. Sorry. Okay, yeah. So we know that each SI is countable. That means that there exists a 1-to-1 and onto function from the natural numbers to the set SI. But this is like kind of like, there exists. That doesn't tell us which one we can choose naturally, So just because there exists doesn't mean that we kind of get it for free. This is why we need to use the axiom of choice, right? So the problem is we have to express this. We have to express our choosing of this function as like a choice function. Okay. So we have each little si is in this set. So we want to choose a function, have a function f from the natural numbers to to the set of functions from the natural numbers, from the union of all the SIs, like that, such that f of I is 1-to-1 and onto f of I going from the natural numbers to SI. Okay, I guess this is like confusing me a little bit, but it's okay. I guess like my problem is like, what am I choosing from? I guess I want to choose for each I want to choose a 1-to-1 and onto function from the natural numbers to SI. Okay, so I might call that x sub I to be all the functions s from the natural numbers to si that are 1-to-1, s is 1-to-1 and onto. And now I want to choose, for each I want to choose an element of this, and that is my choice function. Okay, I think that is making more sense to me now. Okay, and once you choose for each I, you choose a one-to-one and onto function from the natural numbers to si. Then what do you get? Well, you get a for each natural number, you have a function from the natural numbers to si. That means you have a function from the Cartesian product of the natural numbers with the natural numbers to all the si's, and this is 1-to-1 and onto. Such that f is 1-to-1 and onto, right? Because you define what do? You kind of your function is, once you choose a function for each si, you have like S0 looks like S0, 0, S0, 1, S0, 2, so on. And then S1 looks like S1, 0, S1, 1, S1, 2, and so on. And S2 looks like S2, 0, S2, 1, S2, 2, and so on. Okay. And this gives you your function from the Cartesian product of the natural numbers to the union of all the s's. And then you just do what you do for the Cartesian product. You do this thing to reach all the elements. Okay. But the problem is that in order to write each si in this order, you need to choose an ordering for each one, and that choice, that's where the axiom of choice comes in. I hope that some of that made sense in the end. Okay. Okay. But it just goes to kind of show you that there's like things which sometimes seem obvious aren't. Okay. Okay, and then the last thing, something I want to mention is, I mentioned there's like, when we mentioned the axiom of choice, there's 3 different things we might be talking about. There's like the axiom of choice, the well-ordering principle, and this thing called Zorn's lemma. These are all like equivalent in some sense, even though they have different, one is a lemma, one is a principle, and one is an axiom. They're really all axioms. Okay, so it's not really a lemma. That's just its weird name. Okay, this is just a name. And the well-ordering principle is not really a principle. It's also an axiom. Okay. Okay, but we'll call it Zorn's lemma. Okay, and it says that if we have a partially ordered set, okay, suppose that every non-empty chain in S has an upper bound I guess I need to say that S is non-empty. So let me put that assumption in too. Then if every non-empty chain has an upper bound, then S has a maximal element. Okay. Okay. It just turns out that, okay, so first let me say this theorem. Like the other axioms of set theory being fixed were like, we'll just put like, we'll just state it roughly like the following are equivalent: axiom of choice, Zorn's lemma, the well-ordering principle. And when I say that, like, I mean like fix the other axioms of set theory, like don't change those, but take the other axioms of set theory and then assume the axiom of choice, then you can prove Zorn's lemma. Take the other axioms of set theory without the axiom of a choice, but assume Zorn's lemma, then you can show that the well-ordering principle holds, like that kind of thing. So okay. And just for your information, often we might see like Zorn's lemma come up in algebra. It's just because it happens to be more convenient for a certain algebra theorems you want to prove. Because having a maximal element is like a very algebraic thing, I guess. Okay. So I guess on Wednesday, we'll start off with a couple examples of that. Okay. I guess that is it for today. Okay, so let's see, what do I have to remind you of? I think something. Oh yeah, let me remind you that there is assignment 6 due on Wednesday. So if you have any questions about that, please email me. Or if you just like want some reassurance as to how things are going in your solutions, you can also email me. Okay. And then let me also remind you that exam 2 is on April 12th. Okay. I guess that is it for me. Thank you guys for staying with it. And I'll see you guys on Wednesday. I guess tomorrow's a holiday, so have a good holiday. And see you guys on Wednesday. Okay. Bye.